Hello everyone. So in this video, I'd like to talk about the squeeze rule. So this is yet another strategy for finding the more complicated limits. And basically the idea is that we want to find the limit of some complicated expression. And the way to do that is to compare it to something similar, which is simpler and it has the same limit. Okay, so let's see how that works. And before we get there, let's look at a warm-up, which is called the limit comparison. So what is the idea? Well, let's suppose we have two functions, f and g, and we know that when x is close to a, always f of x is less than or equal to g of x. So somehow f is a small function and g is a larger function. And let's suppose we know that at a, the limit of f and the limit of g, they both exist. So we're already assuming the limit of f and the limit of g exist at a. Then if f is smaller than g, well, it follows that the limit of f is smaller than the limit of g. Okay, and that kind of makes sense, right? If we think if the values of f are always less than the corresponding values of g, then with the limit as x tends to a of f of x, we're looking at some number that f gets close to as x gets close to a. With the limit of g, we're looking at what g gets close to when x gets close to a. Well, if the values of f are always less than the value of g, then whatever f gets close to has to be less than whatever g gets close to, just very roughly. Okay, so it makes sense. But notice here it has a disadvantage that already we have to assume that both of the limits exist. Okay, so what about, for instance, if we have a problem with a complicated function, we're trying to discover if the limit exists, and if so, we're trying to calculate that limit. Okay, this is not good enough. This is just a warm-up. So let's get on to the squeeze theorem. And okay, what is the idea? Well, you can kind of guess from the name squeeze theorem that the function we're interested in is going to somehow be squeezed between a smaller function and a larger function. So let's suppose we have three functions. F is less than g is less than h. So we have a small function, a medium function, and a larger function when x is close to a. So we don't care what's happening far away from a, but at least we have this ordering when x is close to a. And let's suppose the limit of the small function and the limit of the big function exist and they're equal. Then the limit of the middle function exists and it's equal to the same number L. Okay, so here it has the advantage of we don't start by assuming the limit of the middle function exists, we get that out of it and we get the value out of it. So typically how we're going to apply this, we're going to start with some function where we're going to try to use a squeeze rule. That's going to be our middle function. And then we have to figure out a smaller function and a larger function that are somehow easier to analyze and they have the same limit. We calculate the limits of those separately, and okay, if they did have the same limit, then we know the limit of our middle function that we're interested in. Okay, and we don't care what happens when x equals a, as I already said. Okay, so here's the squeeze theorem in a picture. So we have a small function f, which is relatively simple. We have a large function h, which is relatively simple. And then we have a function in the middle, which is somehow squeezed, called g. And it's squeezed in such a way that at the limit point we're interested in, all the three functions are, they have the same limit. Well, if we can work out the limit of h and we can work out the limit of f, then our middle function is kind of squished in the middle, so the limit will be the same. Okay, but notice here we're assuming the limit of f, our small function, and the limit of h, our big function, must exist and they must be the same in order for us to squeeze our middle function in the middle and have the same limit. Okay, so let's see how that works in an example. So here, for instance, let's try to find the limit as x tends to 0 of x squared cosine of 1 over x. So it looks like a very complicated function. For instance, we can't use we can't say the limit of a product is the product of the limits, because if we just look at limit as x tends to 0 of cosine 1 over x, you can check that actually this limit does not exist. Okay, so using the product rule for limits is not available here. So we have to do something separate. And if we try to think what's causing the problems, well, the first part, the x squared part, is always, as x tends to 0, the x squared part is going to 0. But the cosine of 1 over x part, as x is getting close to 0, that moves up and down very quickly between 1 and minus 1. So that somehow keeps oscillating between 1 and minus 1. So the cosine of 1 over x part is the problem. So really we want to get rid of that and compare this function to something else that doesn't have cosine 1 over x. Okay, so how can we do that? So here is going to be a standard trick. That one thing we always know about sine and cosine is that sine of anything and cosine of anything, they're always between minus 1 and 1. Right, so cosine theta is between minus 1 and 1, but whatever theta is, whatever is the argument, it's always going to be between minus 1 and 1. So even though the argument here is 1 over x, we can say that cosine of 1 over x is between minus 1 and 1. Okay, so what we're trying to do is we're trying to replace x squared cosine of 1 over x by we're trying to compare it to a smaller function and a larger function. We need to come up with some inequalities. Okay, we're trying to get rid of the cosine 1 over x. What do we know about cosine of 1 over x? Well, we know a smaller function is minus 1 and a larger function is plus 1. And now, okay, going back to our original problem, we're trying to analyze x squared cosine 1 over x. So let's try to find a smaller function and a large function for x squared cosine 1 over x. Okay, well, we can do that based on what we just wrote for cosine of 1 over x, right? If we multiply every part of this inequality by x squared is always positive, so that's not going to change the inequality. Remember, if we multiply by positive things, the inequality stays the same. If we multiply by negative things, it reverses. So we can multiply both sides by x squared. And now we're in good shape, right? Because we have the function we're interested in the middle. Then we have a smaller function minus x squared, which is always smaller. We have a larger function x squared, which is always larger. And the smaller and the larger function are easier to analyze, but the middle function is the complicated thing we're interested in. So let's look at the limit of the smaller or the larger function. Okay, we're looking at as x tends to 0, x squared. Okay, it's a polynomial. We can use direct substitution. It becomes 0. 0 squared is 0. And the same thing with minus x squared. So the limit of the small function and the large function are both 0. So by the squeeze rule, we have three functions, a small one, a medium one, a large one. The limit of the small one and the limit of the large one are equal. The squeeze theorem says the middle function is squeezed in between, so the limit of the middle function exists, and it's equal to the common value. So it's equal to 0. Okay, so using this, we managed to find the limit of x squared cosine 1 over x. And here it is in a very primitive picture. So the function x squared cosine of 1 over x, what is happening is the peaks are getting less and less peaky, but it's oscillating faster and faster. And it's trapped somehow between x squared and between minus x squared, just as we had in the inequality. And we know that x squared is going to 0 as x goes to 0, minus x squared is going to 0 as x goes to 0. X squared cosine 1 over x is kind of trapped between them. Okay, as x goes to 0, even though x squared cosine 1 over x is moving up and down, it's still going to 0 as x goes to 0. So the picture confirms the application of the squeeze theorem that we just did. Okay, here's another type of problem we might see with the squeeze theorem. So suppose we're given some function g of x. Well, we're not given a formula for it. We don't know what function it is, but we're told some bounds for g. So we're told that g is somewhere between 2x and x to the 4 minus x squared plus 2x for all x. Try to find the limit as x goes to 1 of g of x. If you see any problem like this, then it's screaming out for you to use the squeeze rule, because there's a small function, there's a medium function, there's a large function. So let's try to see what is the limit of the small function, what is the limit of the large function, and hopefully see if they agree. Okay, well, both the small function and the large function, we're lucky they're polynomials, right? So to find the limit as x tends to 1, we can do direct substitution, and it turns out both of the limits are 2. Okay, so the limit of the small function is the same as the limit of the large function. It's equal to 2. The function we're interested in is trapped in between, so the limit of the middle function is going to be equal to the common value. It's also going to be equal to 2 by the squeeze rule. Okay, but please notice here that it was very important we were taking the limit as x tends to 1, and at 1, both of the small and the large limits were equal. They were equal to 2. Suppose instead we were given the same data, and we were asked about the limit as x tends to 0 of g of x. So instead of x tends to 1, x tends to 0. Then we would try to do the same thing, right? We would look at 2x as x goes to 0, that would go to 0. We'd look at x to the 4 minus x squared plus 2. As x goes to 0, that would go to 2. Okay, the small function will be going to 0, the large function will be going to 2. They are not equal. We can't say anything by the squeeze rule. So with this information, we would not be able to use the squeeze rule to say anything about the limit as x tends to 0. Actually, whatever rule you use, this is not enough to say anything about the limit as x goes to 0. So with the squeeze rule, we really care a lot. It's very important that the limit of the small function and the limit of the large function agree. Only then can we say the limit of the middle function exists and it's the same. Okay, so in general, the squeeze rule, to apply it, you're starting with some function you want to find the limit of. Typically, it's quite complicated. Try to find a smaller function and a larger function, which have the same limit at the point you're interested in. That will tell you that the function that you have that's trapped in the middle will have that limit as well. Okay, thanks everyone. See you next time.